Okay, so this script is just going to demonstrate how we fit a boundary line model to data using the bolides function in the BLA R package. So the first thing that we do is that we need to load in our library, which is BLA. We also need to load in another library called ApplePack, just to help us do our exploratory analysis. So I'm going to load in my data that I'm going to use. So this data contains two variables, the yield and a soil variable for soil phosphorus. So that's going to be our x variable. Our x variable is soil phosphorus, and our y variable is yield. So I'm going to run these two lines just to assign the soil phosphorus to x and the yield to y. So the first data exploratory analysis that we need to do is to try and check if both variables are normally distributed. And what the function I'm going to use is called the SummaStat function. And the argument that I enter is a variable that I need to check. So in this case, I'll start with x. So I can run that one. It gives me two plots and some data summaries here. So the one I'm interested in is the octal skewness. For us to assume that this data was from a normal distribution, this value needs to be between minus 0.2 and 0.2. So in this case, it's between those two ranges. So we can say that this data is from a normal distribution. I'll do the same for y. Yeah, so for y, it's also 0.19, just at the border of the two ranges. So it's 0.19 and it's less than 0.2. So that's okay. So the next thing that I need to do now is to check for outliers in my data, and I'm going to use the bug plot. So if I run the bug plot function using the data, so the data is just what I read in, is my data. So it contains my x and y. So I'm going to run it in a bug plot using this line. So this is the bug plot. So 50% of the data will be in this dark blue section, and the data that is outside the bag. So this the dark blue one is called the bag. It's similar to the interquartile range when you're looking at box plot. So 50% of the data is found in this uh, area. The light blue section is called the loop. So this is data that is outside outside the bag, but within the uh, yeah. So it's data outside the bag, but not outliers. And anything else that is outside this light blue area, we'll consider them to be outliers. But in this case, you can see that there are no outliers. So we'll uh, we'll proceed. So we need to fit the boundary line to our data using uh, the bolides method. Uh, so the bolides method uses an optimization function to fit the boundary line model to your data. So the first thing that we need to do is to check our data and check which points are at the boundary. So when we use the bolides function, when we enter our x variable and our y variable, and on the model, if we put explore, what it will do is that it's going to show us which of the points from our data are considered to be the boundary points. So if I run this function, so it shows me the boundary points in red. So these are the data points that completely enclose my data. So I'll need to, if I need to fit a boundary line model, I need to fit it to these points because they're the ones which occur at the boundary. Now, like I said, the bolides, as well as other boundary line fitting methods, they use an optimization method to fit the boundary line. So this can be the BF GS algorithm and other algorithms. So basically what happens is that you need, for a particular boundary model that you want to fit, you need to give it some initial starting values for that particular model, and then it goes on to search in this in space to see which parameters of that model that you've chosen are optimal given your data set. So looking at our data, it looks like it follows uh, uh, a, a trapezium model because it goes up and then it plateaus and then it goes down. So we're going to fit a trapezium model. So for us to get some starting values, we need to use the function start values, and in the argument we put trapezium, and then we can run this. After we run, it says select 4 points on the plot that make up the trapezium model in ascending order of x. So I need to go to my plot section and I need to plot to click 4 points that make up the trapezium model. So I'll start from this point. I'll click here. I'll go up. I'll click somewhere there. Then it plateaus up to there. And then it goes down up to there. So immediately I click those 4 points, I'll have in my console some values will appear. So the first value is the plateau value. Then I have my two intercept values. So one on the rising side, which is this one. So the intercept down there. And the other one is for the the descending side, that one. So the intercept should be up there. Then I have the two slopes. So 1.2 on the left-hand side and 2.57 on the descending side. So I need to create a vector called start, and I enter these values. So the first value I need to enter is the intercept on the left-hand side. So just copy that, enter it there. Then I'll enter the next value should be my slope on the left hand side, which is that one. I copy it, I place it there. Then the next value is my plateau value. So I'll just copy it there and I'll enter it there. Then I'll have my second intercept. Just copy it there and it there. And then I have my second slope, which is that one. So I'll just enter it there. So I can run this. And these will be my initial starting values where the function will start looking for the optimized uh, parameters for the boundary model that I want to fit. So now I want to use the bolides method to fit the boundary line. So the bolides method, so the function is bolides, and I enter my x and my y variables, which is the soil phosphorus and my yield. Then I need to specify my start values. So my start values will be equal to this to start because I had this vector which I assigned a start. So start to be equal to start. And then the model, I'll put trapezium because I want to fit a trapezium model. Then this is just a point character. So we use the point character of 16 and the color should be gray. And I'll label my X and Y axis as wheat yield and so P. So I'll run this to see how it fits my model. So as you can see, once I run that function, it gives me an output. It tells me I have fitted a trapezium model. Then it gives me the equation of that trapezium model and the actual fitted parameters. So this is the first intercept, the slope, first slope, and then the plateau value, second intercept, and the second slope. It also gives me the value of the residues based on the model that it has fitted to my data. So that's how we can fit a boundary line model to data using the bolides method. One thing to note is that this, like I said, it uses an optimization function to check for which uh, uh, model parameters are optimum. So once you give it starting values, it starts from that particular point and it keeps on searching until uh, it finds boundary line parameters that have the lowest sum of squares or residues. So this process sometimes may be sensitive to starting values because some starting values, as it is searching for optimum values, it might get stuck in some areas, and hence it will give you an answer or an output that is not really what is supposed to be because it got stuck as it is moving, checking for uh, parameters. So what they recommend is that instead of using one start value, you use multiple starting values. So in this case, here where you have start, instead of just using one vector, you can use maybe 10 starting values. And then you run them and then you select the one which has the lowest uh, uh, residues as your model. So that's it. That's it for this session on how to fit the boundary line using the bolides algorithm. Thank you.